Morning, everybody. All right, let's get started. And once we've done the simulation, we can have a look at the autosave options. Right, so let's start our new simulation. Oh, I was clicking on the presentation, not on the actual app. Okay, so you're all familiar with this, so we can do next. And I must just get up my crib notes. Okay, so we want to do carbon monoxide. Let's see if CO works. Yep, CO works. Hydrogen. Come on, thank you. And methanol. And when that's done, it's always a good thing to clear your space, because then it's going to show you the compounds that you've chosen, so you can be sure that you've got everything you wanted. Right, and then let me just check. Right, Ping, Robinson, and NRTL in that order, because the first one you put in is the default. So that one, add, and NRTL, add. Next, you see, you notice there it puts Ping Robinson. Well, you can't see yet. You can see there when I hover over it, Ping Robinson 1 and NRTL is 2. I don't think we are going to use NRTL because when I switched to NRTL on the gas liquid separator, I didn't find much difference in the results. So, but NRTL is a better thing for polar compounds like methanol. Right, and then we go to our normal units, C5, finish. And now we are ready to put in a reactor. So we are going to choose reactors and a conversion reactor, and we're going to drag it onto the screen. And now we can make all of we can add streams to that. So we select it, add an inlet stream, outlet stream 1, outlet stream 2, and an energy stream. I always like to move that energy stream so that it's got a decent looking, doesn't go in circles. All right, so that's blue, which means it's solving already, and there you can see that whether it's solved. Last run execution time 0.1464, and it turned blue. So the next thing we need to do is to add the reactions. So now actually you're going to find that these things are going to have the same inlet. Oh, no, we're not going to do reactions yet. We're going to first change the inlet composition. So this MS3R it's still got, it hasn't changed from the inlet. So let's change the inlet. Click there, get our inlet on this side. And the thing that we want to change is the amounts of the various compounds, because DWSim will always assign an equal amount to each of the compounds going in, and we don't want methanol going in. So there we want carbon monoxide to stay at 0.33. We want no methanol. I'll put in a 0, and it is important to press enter. You can't just change your focus. If I change the focus to the next one that I want to change, hydrogen, I want to be 0.66. it doesn't enter the 0. So you have to hit enter, and then we can change this one 0.666666. I'm going to do it this way. I could have put a 7 there, and then I can just say normalize, and that changes the 3 to a 4. It would have been better changing the 6 to a 7, but that's fine. It's just to recognize that the normalize would be, and then don't forget accept changes. Again, the mistake I've made when I first did this. All right, let's just see, change compound amount, setting methanol, accept changes. Now we need to enter the reaction. So we're quite happy with the conditions. I do want to change the conditions of the reactor. So let me change the conditions. The temperature of the reactor. Oh no, it's not the temperature of this is the temperature of the inlet stream. Sorry, right? So we leave it like that. And now we want to enter reactions. And this is where it's really important to recognize that settings on the ribbon bar on the top. Because settings, if we open that, by the way, please interrupt or send. I didn't hear the latest chat come in. But please interrupt me if you're not following or if I've done something wrong, obviously wrong. Okay, so here is my settings. It's opened on my other screen, so I'm just going to drag it up. So this is a very important dialog box because it's got the compounds. Here's the, so if you wanted to add extra compounds, and you often do, you can go and search for compounds and add them onto your list. So Thermodynamics, it will have what we've chosen, Ping Robinson and NRTL, and the system of units, it will show that we've chosen C5. So let's go to the reactions. Now you'll see two things. You can have a reaction set or a chemical reaction. Now, at first, I wanted to do a reaction set and then add the chemical reactions that go with that reaction set. But that's not the way it should work. You have to add a chemical reaction first, or a number of chemical reactions, and then you can make a group. So you can group, if let's say you've got 5 chemical reactions down here, and you want to group for one particular reactor, you want to group 2 of the reactions together. Let's say it's methanol synthesis and it's water gas shift. You would make a new default set, and then you would add them. You would add whichever 2 out of this list down here, you'd add to your new default set, to your new reaction set. So you can make several reaction sets and use them for different reactors. But we only need the default set at the moment, so we're going to just add a conversion reaction, chemical reaction. Okay, and again, it's opened on my other screen, so I'll drag that up. And we can give it a name. So this is methanol synthesis. And we can give it a description if we want to, yeah. Now, we're going to include all 3 of these. And we're going to choose which one is the base component, because the base component is what you base your conversion on, because conversion always relates to a single component and how much of it you use up. So normally with syngas from a gasifier, you will have a hydrogen divided by carbon monoxide ratio of less than 2. And therefore hydrogen would be if you react them in a 2-to-1 ratio, as we need to do over here, let's just put in the stoichiometric coefficients. It's -1 carbon monoxide and it's -2 hydrogens will give you methanol +1. When you react hydrogen and carbon monoxide, you want to base the conversion on the one that is the minimum stoichiometrically. So if we've got 1 kilomole per hour of hydrogen and 1 kilomole per hour of carbon monoxide going in, the hydrogen will be used up first. So you want to base your conversion on that one. Otherwise, if you base it on carbon monoxide, if you have a conversion of 60%, you will use up 0.6 moles of carbon monoxide, and for that you would need 1.2 moles of hydrogen, and you don't have that much, and then you get an error. So that's why we want to base the base component. Where's the base component? There it is. Base component is now hydrogen, and the stoichiometry, the program is checked, is correct. So that then you get an OK over there, and then just looking. I'm just looking if there are any comments because I'm getting notifications on my phone. Base component, and then the conversion. And in most cases, we enter fractions as fractions, but in this case, it's asking for conversion as a percentage. So we put in 70% there. I think we are complete for this thing, for this dialog box. There, the phase is going to be in the vapor phase. Not sure that makes that much difference, but it might make a difference to the thermodynamics. And then we can say, OK. And now we've got a reaction, a chemical reaction that can be associated with our reactor. OK, so let's close the settings for now. And we choose the reactor. The reaction set is the default set, and that will have the methanol reactor included. Now I want to choose the temperature at which this reactor operates. So I'm not going to use adiabatic. I don't think isothermic is the right word. I'm sure isothermal is the right word. Anyway, I'm going to define the outlet temperature, and that's going to be 250 degrees C. And now I must hit enter. Again, something that I have not done. So there's the delta T is correct now. And now let's hover over this. Yes, you can see at the bottom box, it says MSTR03 is at 250 degrees C. The pressure, I want to change the pressure over here because I want to leave the pressure drop as 0. It's very useful if you've got a complex flow sheet. Until the pressure changes, you don't want to. If you need to change the pressure of your system, and you've got a whole lot of succeeding unit operations, you only want to change the pressure at one place. So if you choose all of them to be a pressure drop of 0 bar or whatever small pressure drop you'd like to put in there, if you're using pressure drop instead of absolute pressure, you only have to change the pressure at one point. So I'm going to change the pressure over here, and that's going to be 20 bar pressure. Now you can see it's run properly, and if we look at, let's look at the vapor this time, we've got 250 degrees C and 20 bar on the bottom box. So that is correct. It's taken this pressure and it's propagated it through because in the actual reactor we've said that the pressure drop is 0 bar. So this thing seems to be working correctly at this stage. Let me go and look at my script notes again. The PDF that I posted this morning. Add a new chemical reaction, that's fine, we got there, we finished with that dialog box. Return to, and we define outlet pressure. And now we can drag and drop, so we're done. Mass flow of methanol should be 2520 kilograms per hour. Let's have a look at 2, and no, I'm not getting. I'm just going to drag this whole thing downwards. Get the top thing. Oh, who's calling? I'll reject that one. Let me just see comments. So will our base component always be the reactant with the highest stoichiometric coefficient? No, not the highest stoichiometric coefficient. It will be the one that's got that will run out first if you react according to stoichiometry. Okay, if somebody from the class was calling me, rather put it on the comments. Okay, so let me get back to my notes. We're about to put in a separator, gas liquid separator, and we chuck it in over there because it's going to be connected to the gas line here. So in the past, we just added, let's choose it first. We added all of the streams. In this case, we are not going to add the feed stream because we've already got a feed stream. We're going to take this stream and use it as a feed stream for the separator. So inlet stream 1, we're going to, well, let's do it immediately, is going to be MSTRO2. And we've got 2 exit streams, a vapor stream, which we'll create. And it's got a light liquid stream, which we'll create. And we need to put in an energy stream over there. And I move it so that it's got a decent looking line. Okay. Right, let's have a look at the conditions of this MSTRO4. Choose it, and we have a look at temperature and pressure we'd like to set. So we override temperature and we make it 40 degrees C. Now the reason I'm making it 40 degrees C is because with cooling water, you can expect your cooling water to be 30 degrees C, and we generally want a 10 degrees C temperature difference in your heat exchanger. So you can happily cool down a stream, any stream from a reactor, from whatever, you can cool down to about 40 degrees C without using refrigeration. Remember, we talked about that in our lecture with the vinyl chloride monomer example. So that's why I choose 40 degrees C. We override the separation. Oh, wait a minute. You see there, I didn't press enter. 40, enter. Right. And then pressure is I'm going to use 10 bar pressure. I want it to be high enough that I don't lose too much out of MSTRO4, out of the gas. I want it cooled so that we liquefy the methanol, but all of the unreacted syngas must go out at MSTRO4. So that's why I'm choosing about 10 bar. It's a medium low pressure. And oh, no, I didn't press enter. 10 bar, enter. Okay. So let's have a look at the stream coming out. And we've got 40 degrees C, 10 bar, so it's all calculating correctly. And then we can go and look at the amounts. And mole fractions don't mean that much to me, except yes, there's very little methanol coming out. So I would rather go to, instead of mole fractions over here, Why don't I have the ability to change the mole fractions to?
You have to go to results.
Thank you. I love that. Somebody just piping up and helping me there. Thank you. So it is properties, mole fractions. We want to look at mole flows, and there we go. So 3.82 methanol is being lost here, but you can see it's a relatively low molar flow. Oh, let's go mass flows rather. Mass flows, kilograms per hour. 122 is being lost, and but there's plenty that's in comparison with the rest. It's not too bad. So let's have a look at this one, and again we need to go to results, phase property results, not phase properties, compounds properties, amounts, compounds amounts, mass flows. And there you can see, so we've got 22,400 odd kilograms per hour of methanol in the liquid phase. So in comparison with the other one, the mass flow is 1,200, or the mass flow of, let's see if we're still on the same page. No, we're not. 2,400 versus 122. So, you know, it's not a huge loss of methanol over there. But again, it illustrates that when you want to do a separation, even with the separation of essentially non-condensable gases, carbon monoxide and hydrogen, from a highly condensable methanol, you still don't get a really good separation. So this is what 1 in 24. 1 in 24. So that's like 4% that we're losing. And that's at the best possible condition. So generally, in process synthesis, when you need to separate, you should use a distillation column. It's interesting in this case, though, a distillation column would not really be viable because we need to liquefy at least CO, and CO has got a very low boiling point. So we would not be able to use we would not be able to use a distillation column in this case. So we'll do this, and let's have a look again at this MSTR05 and have a look at the mole fractions of monoxide and hydrogen in the 99.8% molar methanol. Now that you can put into a distillation column with a partial condenser. And this will be again one of those heuristics that we'll be doing later on in CPS. So let me get my crib notes again and see if I've covered everything we said we'd cover in this thing. Adding a stream table. Oh, a stream table. Now, William Bosch actually showed a better way on the first Tut. That essentially you can insert a property table or a master property table. Now I inserted a property table, which wasn't that great. Double click, and then you choose for each of these things. You choose, yes, that's an energy stream. I want to see what is the duty of that reactor. And then for each of these in turn, I want temperature, pressure, mass flow. So I'm doing it manually, but I'm sure there are shortcut ways that maybe somebody can pipe up and suggest. Temperature, pressure, mass flow for all of the streams. Temperature, pressure, mass flow. And now I'm going to show you on the reactor, you can look at different things, but none of these is going to be particularly useful. Hydrogen conversion should be 70%, and methanol conversion will be also 70% because it was stoichiometric with the hydrogen. So yeah, I didn't find anything particularly useful there. Yeah, you can say vessel orientation. You can choose that as an option on that vessel. operating pressure, we know what it is. We set that, so there's not much use over there. And then once you've done that, you can simply close it. It's strange that there's no OK, but you can close it, and there you get your properties table. So that's a very useful thing to have, because then as you change things on your flow sheet, you can immediately see them without hovering over the various streams, as we've done in the past. So we can check that the pressure goes 20, 20, 20, 10. 10. These are the two 10s on the end over there. And all the pressures are right. 3,600 kilograms per hour, essentially all the way through. And then the mass flow of methanol at the bottom here, 2,400 out of 3,600. So that gives you an idea of that 70% conversion. Okay. Yeah, and that's it. That is today's Tut, really. So post some questions. I am going to now have an experiment and have a look at the file. Wait a minute, let's just look for file save options. I'm first going to look at settings. No, there's not a lot on miscellaneous settings. So it won't be floating tables and property lists. Mass and energy balances. Never mind. This is very useful because that's what I ask you to do in the tolerance to the mass and energy balances. That's what I ask you to do in CPJ, that you must actually formally look at the mass and energy balances, because sometimes simulation packages don't converge properly, and it's good for you to check that the mass and energy balance is actually balanced. And what you'll find is, certainly if you change your unit, your properties package from one unit operation to the next one, you're going to find that, for instance, that stream always does a flash and before it enters, and then if you suddenly switch to a new properties package, you might find that your energy balance doesn't balance anymore, because your duty is going to be worked out at with the one thermo package, and the stream is calculated with another energy package. Okay, right, so let's have a look under file save as. I just wanted, I have learned a little bit about this thing, and that is over here I've got I created a new folder, DWSim simulations. So you can choose new folder and choose your thing, and then it always saves under that. This is ethanol water. This one is yeah, okay. It will always say once you first, ethanol water was our Tut one. That's why I called it ethanol water. I should just call it Tuts. I should rename that one Tuts. But now whenever I save, it defaults to the last one that I saved at. So that's quite useful. So you just have to create a new folder and then give it a new name. I'm going to actually type in Tut2 methanol. And if I say save, it's going to say, must I override? You want to replace it, and let's say yes, because this one seems to be working fine. Yes, so you can change the system units while you're modeling. Yeah, it's no problem, because it saves them consistent. It saves them in a consistent set of units internally, and whenever it displays, it simply does the conversion. Kinetics, yeah, kinetics. Who's asking that? Adding kinetics to the reactions, Jared. It depends on the reactor. So let's go to the reactors. So some of these reactors, the CSTR will have kinetics, have the option of doing kinetics, and a plug flow reactor will have. So you can have those two, where you will need to support kinetic and HET reactions. Let's just look here. Supports kinetic and HET. Equilibrium reactor is typically, yeah, you can put in your own constants, your equilibrium constants. Gibbs reactor takes all of your components and it minimizes the Gibbs free energy. In other words, that would be all of the components going to equilibrium at the conditions that you specify for that reactor. So this is one that I use pretty often, but the most often is a conversion reactor, because you don't want, let's go to a continuous stirred tank. Now, where is it? Oh, wait, I have to put it onto the screen and click it. Now you're going to be restricted to the type of reactions that you have. So your reactions, you'd have to go and put into the reaction thing, and you'd have to put in a very specific, a power law reaction. But most, well, certainly most catalytic reactions have fairly complex kinetics. So you won't find those complex kinetics in this package, in DWSim. And that's why I'm always going to recommend, when you're doing DWSim, you use conversion reactors, and you set your conversion to be less than at least what the Gibbs reactor would predict. In other words, less than equilibrium conversion. And then you can go and design your reactor using Python or whatever you choose. Delete that. Let's just go to reactions. Oh, there's a new thing. Let's go to reactions. And we put in a new reaction. And this time it's going to be kinetic. Oh, right. The dialog box is not on your screen. So there's a base component. There's the equation. And there's Arrhenius constants, A and E, simple or advanced kinetic specification. So yeah, oh, Python script, that's very nice. All right, well, now you guys are really off and running. Yeah, so you would be able to do that. It's going to make because you're solving a fairly complex differential equation. If it's going to be a plug flow reactor, you're going to be solving a complex differential equation with your Python script. Your simulation is going to take long. So whenever you enter something, it's going to solve. Whenever you change something, it's going to automatically solve, and that might take some time. And in that case, you want to switch off this thing. You can switch off flow sheet calculator active or not. Oh wait, I think it's that thing. You switch it off. So then for solve, there's a way of switching off the automatic solving. I wonder if that's it. Abort solver. But yeah, as soon as you've got a complex flow sheet, it might take too long and really impede your progress, because it's taking more than 0.12 seconds to solve the flow sheet. Then you want to pause the solver, do stuff, and then eventually say yes, force solve. which is easily done with F5. So then whenever you want to solve the flow sheet, you just press your F5 and get your results. Right, let's have a look at other things. Assuming we are trying to minimize the amount of methanol lost, would we use a cooler? Yeah, I guess we could use MSTR04 to cool the MSTR04 because we've got most of the stuff out and we want to just scrub out the rest. But talking of scrubbing, that might be an option. We'll be talking about it in CPS later. What you can do to use separation. So we're talking about this one, MSTR4, which has got a little bit of methanol in, and how do we recover that little bit of methanol? And that will use let's see if I can draw on the screen. It will use a column. Let's call it a packed column. And from the top, you'll put in water that trickles down the column. From the bottom, you'll put in MSTR04. So MSTR04 consists mainly of carbon monoxide and hydrogen, and that will go out at the top of the column, countercurrent to the water that's coming down, and the water will dissolve the methanol, and then you'll get almost 100% conversion of your methanol. So I think that would be the answer to recovering your methanol by stripping it out with methanol. Yeah, it's a stripper. There's a stripper, and the other one is an absorption column or something like that. Right, let's have a look at comments. We would want the pressure out of the conversion reactor to be lower than the pressure of the separator. Yes, higher. Yes. The reactor must be higher because you don't want to, because certainly by the time it exits the reactor, it will be vapor, and you don't want to compress a vapor. So you will typically always choose the reactor, which occurs typically early on in the process, to be a higher pressure than all of the subsequent separations. How do you properly add a recycle stream? Yeah, that's coming later. When you add a recycle stream, it can cause problems. So to properly add a recycle stream, this is something that you would want to recycle. You'd go to a splitter so that you can have a purge. If you don't put a splitter in, you can get this. You can confuse your simulation because if you've got a slight remember when we put in the hydrogen and the carbon monoxide here, we use 0.3334 and 0.6660, and because of that slight difference in the stoichiometry, if we recycle this totally without having a purge, we're going to build up one of those two. We're going to build up the CO in the system, and your thing is not going to solve. So it is important to first put this through a splitter, and then you can recycle most. So the splitter might have 10% split off, and the rest, 90%, you pull back and put it back into the reactor. And then it's quite okay to actually put the methanol back into the reactor. And of course, then with only 10% going out, there you can put it through a stripper and take out the very last. Now it's only 10% of that little bit of methanol that you're losing. But yes, we're going to do recycles in a separate tut because they cause problems. But certainly, as soon as you do a recycle, you must have a splitter. All right, I think that's a good time to close off. I'll just find out where to stop recording.